Well, all the expressions which we derived, or I derived for you, just before for dipole moment, polarizability, shielding and spin-spin coupling constant were using perturbation theory. And I shortly discussed that using perturbation theory implies that you have solved the unperturbed problem. But quite different to monoprecip perturbation theory, where the unperturbed problem is the Hartree-Fock equations, which we have solved, although we actually didn't solve them either, because we only solved them in a finite basis set, which you could argue for is cheating, but because you solved them approximately. The same we have here, that here the unperturbed problem is just the solution to the Schrödinger equation, and that we definitely did not solve exactly. We can solve it with all the approximate methods we do, but there's sort of this issue that those expressions which are derived, they are exact if we know the exact unperturbed states. So let's look at some alternatives to that, and that is, let's do derivatives but without perturbation theory. Without perturbation theory. And that brings us to something which is called the Hellmann Feynman theorem. And let's now look again. First, let's look at exact states. So, let's say we have Hellmann-Feynman theorem is general in the way it does not only apply to this kind of external field, magnetic moments, it applies to anything, any kind of parameter on which our energy depends on. And the big other application of the Hellmann-Feynman theorem is then change in the nuclear coordinate. So this could be a change in the nuclear coordinates, or in general nuclear coordinates also, which in our Born-Hauptmann approximation are parameters in the Hamiltonian, because we fix them to a particular value when we solve the equation, and the solutions are then going to depend on that value. I mean, if we change the nuclear coordinate, we get another Schrödinger equation, we get another energy. And so what we want to look at is what is the derivative of the energy with respect to this parameter lambda. Could be a nuclear coordinate or change in nuclear coordinate, could be electric field, magnetic moment, all that. Now, for the exact states, of course, I would calculate the energy just as the expectation value of my Hamiltonian. And it was this Hamiltonian which depends on this parameter. And if those are the eigenvectors of this Hamiltonian, the solution to the Schrödinger equation with that Hamiltonian, then they of course depend on this parameter as well. And I want to take the derivative with respect to lambda. And again, like before, the lambda is not one of the integration variables, so therefore I definitely can take the derivative with respect to the lambda, interchange it with the integration, so I get it in. But now I have a product of three contributions, three terms, each of them depending on lambda. So now I really have to use the product rule. And the product rule, if you have three terms, means you're going to get, I mean, if you have a product of three entities, you're going to get three contributions, three terms. Each of them, you take the derivative with respect to one of them. So, now we get the derivative. Let's take here of the wave function in the bra. Then, with respect to the Hamiltonian, so I have lambda, the derivative of the Hamiltonian, with respect to lambda, And finally, the derivative of the wave function in the ket. Oops, here was the derivative. The wave function in the ket. Good, but I said these are exact states. So h of lambda acting on c, which is a function of lambda, is going to give me that energy times the wave function. And I can use that here. I can use that, for example, here. And I can use it also here, because I can now let the Hamiltonian act to the left, or move it into the bra. The Hamiltonian is Hermitian, so when I move it into the bra, the Hermitian conjugate, which I should get in the first place, is the same. So I can again use this. And that means the first term actually gives me the energy, and then here an integral which is the overlap of the derivative of the wave function with the wave function itself. The second one then, that I keep as it is, like this. But I can do the same trick with the last one. And since the energy, the energy is now here in the bra, so in principle it's the complex conjugate when I take it out, but the energy is real, so the complex conjugate of a real number is still a real number. And now I get the overlap between the function and its derivative with respect to lambda. Like this. Good, so let's combine those two terms with the energy. I get this one, and I get a parenthesis of the term where I take the derivative of the bra plus the one where I take the derivative of the ket and I get my term which is the expectation value of the derivative of the Hamiltonian. Like this, and I'm missing the parenthesis. Okay. Now what I can do now, I can combine those two terms, and I can write them as this actually being the derivative of the overlap of the function, like this. This is sort of just like here, but going backwards now. Because if I take the derivative of this integral, I bring it in, this is a product, so I get two terms. I get the derivative of the bra, and I get the derivative of the ket. So that's the same. And then again, for the third time, and now I'm not going to write it again, the expectation value of the derivative of the Hamiltonian. But that is the derivative of the norm of the wave function with respect to this lambda. But lambda is an eigenfunction of my Hamiltonian for every value of lambda, and of course I make sure that this is always normalized. So the derivative of the norm with respect to lambda is just 0. It's not changing, it's always 1. And then I end up with that the derivative of the energy with respect to this parameter lambda which I had included in the Hamiltonian, is actually if I have exact states, meaning states which are my wave functions are actually eigenfunctions of the Hamiltonian. This is just the expectation value of the derivative of the Hamiltonian, which is the Hellmann Feynman theorem. And then if I do that for, like before, I evaluate that derivative for zero value of that parameter, then I just get here, I mean, if I take the derivative, I take the derivative, but the lambdas disappear then for the wave function. So this is the wave function without the lambda, or lambda equals 0. And the derivative of the Hamiltonian with respect to lambda, again evaluate for lambda equal to 0. Like this. And if lambda would have been a perturbation electric field or magnetic field or something like that, in our case, then we end up here with the expectation, the derivative of the energy, which for example is the dipole moment, is the expectation value with the unperturbed states and the derivative of the Hamiltonian. Which means that we actually get precisely the same as we got from perturbation theory. But we didn't use any perturbation theory here. We still, of course, used that we have this one. So we used the same basic assumption that we can, that those are exact states. So if we have exact states, then we get the same as we have in the perturbation theory. So first order properties, derivatives of the energy, are expectation values of the corresponding derivative of the Hamiltonian of the corresponding operators.